In this section, we're going to be looking at the idea of significant figures. Now take a minute to look at the cartoon that you see in front of you, and hopefully you can see the humor in the cartoon. It makes sense why this would be funny. Well, we want to look at why those numbers mean what they do. So we're looking at a number of 200 million germs. We're looking at 99.99% of germs being killed. Okay, 200 million, that's a lot of germs. 99.9% of germs killed. That sounds pretty good. It sounds like, there's only 0.01% of the germs surviving. But when you do the math, 200 million times 0.01, that's a lot of germs left over. So, ew. But, 200 million, 2 million, we want to look at those numbers. What are they telling us? Is that something to be concerned about or not? So what we're going to do is look at how we determine the number of significant figures when we have a piece of data, a number that's been reported to us. Now those significant figures are dealing with values that are being recorded. So when I make a measurement in the lab, I'm going to have, as I said in the previous section, a degree of certainty to which I know that measurement, and then an estimated digit. So with significant figures, that tells me how many of those digits I can actually use. Measurement in the lab, I know that they're all going to be significant. But what if it's not a number that I measured in the lab? What if it's a number that I gained by carrying out a calculation? So for example, I can take my calculator and I can take the number 5012.36 and I can multiply that by the number 1489.23. And when I hit enter, I get 7,464,556.88 ... That's a lot of numbers. Should I write down every number the calculator gives me? Do I presume that the calculator knows best how that measurement was made? Not necessarily. So I want to look at the rules for applying significant figures. Now before I can look at the rules for carrying out the calculations, I need to know how to evaluate a simple number that's been reported to me. Okay? So if I gave you a number, how would you know how many significant figures are in it? And that's what you're seeing in front of you. You're seeing the rules for determining how many significant figures there are in a correctly reported measurement. So first of all, rule number one, if it is a non-zero digit, if it is anything other than 0, you're in good shape. It is significant. Don't have to worry about those. It's just those zeros that get pesky. So let's look at the next set of rules. Number 2, interior zeros. These are zeros that are sandwiched between two non-zero numbers, anywhere in between. So if I have something like 101 Dalmatians, or I have 20,001 leagues under the sea. Sorry, that was a little bit of a stretch. Couldn't think of another number right off the top of my head. But if I have zeros that are between two non-zeros, those are all significant. 101 would have 3 significant figures in it. The 1, the 0, and the 1. 2001, A Space Odyssey, there we go. 2001 has 4 significant figures. The zeros are between two non-zero numbers, 2, 0, 0, 1. Okay, so if they're in between two non-zeros, you count them. They're significant. All right, now let's look at the idea of trailing zeros. Trailing zeros are zeros that are to the right-hand side of a non-zero number. Now, depending on where those trailing zeros are and how the number is set up, they may or may not be significant. Now, if you have trailing zeros and you have a decimal point anywhere in the number, those zeros are significant. So trailing zeros that fall after a decimal point are significant. trailing zeros that fall before a decimal point are significant. Okay. The key word there is decimal point. Gotta have that in there. All right, now I'm going to skip down to rule number 6 really quick. There's one other case you can have with trailing zeros. If you have a trailing zero that's at the end of a number, but there's no decimal point actually physically shown in the number. There's an implied decimal point. Every number has an implied decimal point. But if a zero comes at the end of a number but before the implied decimal point, those zeros are ambiguous. And unless we have clarification, we cannot really assign significant figures to those. So now go back to that 20,000 leagues under the sea. If I gave you the number 20,000, 20000, there's no way of knowing if any of those zeros are significant or not. There's an implied decimal point at the end. I could be talking 19,000 leagues under the sea, 21,000 leagues under the sea. I could be talking 20,489 leagues under the sea. You don't really know from the number. So in that case, the only number we know with certainty as significant is the 2. The zeros are ambiguous. They may be, they may not be. We will try to avoid those sort of cases by applying scientific notation. And again, we talked a little bit about scientific notation in part 1. We can look at that more. That will be picked up in greater detail in the scientific math course. All right, and now back to rule number 5, leading zeros. These are zeros that occur on the left-hand side of the first non-zero number, and they will have a decimal point with them. These are zeros that occur in a number that is less than 1. Okay. Now, leading zeros are not significant. They are only there to locate the decimal point. So for example, let's say I was going to represent the number 5 cents in terms of dollars. So I would say $0.05. Now the only reason the zero is there, 0.05, is to have a zero in order to get out to the hundredths place where we represent pennies, where we represent cents. That zero doesn't really mean anything to us. So we're only using that to get out to that point. Or if you look on some different types of medication, and they'll talk about the amount contains, 0.001% of a particular medicinal compound. The zeros are just there to get out to the place where there is a significant value. So leading zeros are not significant. They don't count. Okay? So we'll look at some examples of that, but now we want to talk about the difference between reported measurements and exact values. So exact values or exact numbers are numbers which are discrete, quantifiable units. They will have an unlimited number of significant figures. We are able to count exactly a discrete object. So that's like the 7 pennies. If I have 7 pennies, I have exactly 7. I could say I have 7.0 pennies, I have 7.000000 pennies. It's 7 pennies. It's exact. So if I have discrete quantities, then I don't use that to limit the number of significant figures. If I have integral numbers, so integrals being whole numbers, 1, 2, 3, 4, if those are part of an equation, I don't use those to limit my number of significant figures. Now we're going to look at the idea of conversion factors, how to get from one unit to another using a conversion factor. That we'll be looking at next week. Conversion factors are sometimes defined quantities, not always. So for example, if we wanted to convert inches into centimeters, 1 inch is equal to 2.54 centimeters. That is exact. 2.540000. I can put as many zeros as I want after the 4. It won't matter. That's an exact number. As opposed to something like pi. If I look at pi, we know that it's 3.1415, and it just goes on until infinity. Those numbers just keep going. So it's not a defined quantity, does not have an unlimited number of significant figures in the value of pi. Some examples of how to determine the number of significant figures in a value. If we look at the first one, 0.0035. 0.0035 to be precise, to show all the zeros they have in there. Now when I look at those are leading zeros. They're only in there in order to get out to the place that we need to start recording values, out to the thousandth place. So all of those leading zeros are not significant. They're just placeholders. So this number has only two significant figures. If I go to the next number, 1.080, I see that, first of all, I have a zero that's sandwiched between two non-zero numbers, between the 1 and the 8, so that one's significant. The next one is a trailing zero, and there's also a decimal point in there. It's after a decimal point, it's after a non-zero digit. That makes it significant. 4 significant figures on this one. The third number, really easy. There's no zeros in there. Everything counts. 4 significant figures. All right, now number 4. They've given you a little bit of a challenge here. They put it in scientific notation. And I don't mean to harp on the fact that, we'll be doing a lot of this in scientific math, but what we want to do in this course is sort of get ourselves up to speed on concepts and move along in chemistry concepts. And so we'll only brush lightly on these, and we'll look at them in more detail in scientific math. But what they're doing with scientific notation is avoiding the issue of ambiguous zeros. So anytime you see a number in scientific notation, all of the integer values that you see here at the beginning, not the exponent has nothing to do with significant figures, all of these integer values are going to count as significant. So in this case, 2.9, that has 2 significant figures. If I had written 2.90, then that 0 would be there for a reason. That would tell me I have 3 significant figures. Now look at the fifth one, 1 dozen. If somebody says they have a dozen of something, they have 12. They can have a dozen eggs, they can have a dozen basketballs, they can have a dozen cars, doesn't matter, they have 12. That's an exact value that has unlimited significant figures. I do not use that to limit myself in a calculation. If I look at this one, 100.00. I have a decimal point and I have lots of trailing zeros. Doesn't matter which side of the decimal point they're on. If I have a decimal point in there, my zeros become significant. Okay? If they're trailing zeros, a decimal point and trailing zeros will be significant. So I have 5 here. Now notice up here I have a decimal point. These are not trailing zeros, they're leading zeros. So those don't count. These do down here. 5 significant figures. And then the last one, 100,000. Well, I really don't know. I have an implied decimal point right here. I wasn't given anything exact. I wasn't told, do I have exactly 100,000 of something? Do I have 99,000 of them? Do I have 100,300? I don't know. That's ambiguous, so I cannot make any determination on the number of significant figures. This number is one that would benefit from being converted into scientific notation. That would alert us to a more precise number of significant figures. Again, we'll take a look at that in the scientific math course. Okay, so now that we know how to look at a number and evaluate the number for significant figures, let's take a look at how we would then put those numbers together in a calculation and then determine the number of significant figures in the final answer. So these are going to be the rules for rounding when I get a final answer. Okay, first of all, anytime I use numbers in a calculation, my result has to be rounded to reflect the significant figures from the data. My final answer cannot be any more precise than the numbers from which it was calculated. If I said that I had 30 basketballs and I was going to multiply that by a mass of air that goes into those basketballs. When I say 30 basketballs times the mass of air in one basketball and punch that in the calculator, I'm probably going to get a number with lots of decimal places in it. The calculator just keeps calculating, keeps spitting it out. How many of those are actually significant? Well, the 30 is precise on the basketball, so it really depends on how we measure the mass of the air. If I used a rough scale that only weighed out to the tenths place, then I'm probably not going to need a lot of those digits. If I used a very precise analytical balance that let me measure the amount of air out to 5 decimal places, then I need to reflect a lot more of those numbers. Depends on how the data was collected. Now, if I'm carrying out a calculation that has more than one step, I want to make sure that I don't round the answer off to the number of significant figures until I am done with all of my calculations. I want to make sure it's only the final answer that gets rounded. I don't want to round off between steps, because what happens is each time I make a rounding determination on a step, that rounding is telling me that I'm uncertain of the last digit. And there might be a little error built into that last estimated number. Well, if I have a little bit of error built in on step 1, and then a little more error built in on step 2, so on and so forth, I'm going to end up with a lot of error at the end. Now, it could be that some of the numbers don't have error, but if every one of them had just a little bit of error, my final number is not going to be anywhere close to what it needs to be. Think about people building a railroad track. And they're going to start on the East Coast and the West Coast, and they want to meet in the middle and have this train track meet. Well, if one of the groups, laying each segment of that railroad track makes a small error each time they lay some track, they're off by ½ an inch when they lay the first 100 miles of track. And then they get off ½ an inch by the time they lay the next 100 miles of track, so on and so forth. Well, if you're going from the East Coast to the West Coast, that's a lot of little errors that are going to get compounded. Do you think those train tracks are going to meet where they need to be in the middle by the time they get together? Probably not with that amount of error. So again, if you're doing more than one calculation within a single problem, wait till your final answer to round your significant figures. Okay, now, next thing we're going to look at, when we've got a number, when we're ready to round, how do we know where to round that thing? You're going to use only the last digit being dropped, or the leftmost digit being dropped, to decide whether to round up or round down. Don't worry about any digits to the right. And this causes a lot of people confusion because they'll want to look at all of the numbers they're dropping and look at how those round up. After a certain point, you just kind of ignore anything further to the right. Now, what am I talking about with that? Let's look at an example. Let's say I carried out a calculation and I got the number 1.6478, and I want to round that off to 3 significant figures. Okay, so I know I have to start at the 1. I'm always going to start from the left. I have to keep the 1, the 6, and the 4. Those are my 3 significant figures I'm going to keep. I have a 7 and an 8 down here. Now, when I decide whether to round the 4 up or down, I don't care about the 8. I'm not looking at that one. All I'm going to look at is the 7. That's the number that determines what I do with my rounding. So 7, and we're going to use the rule for rounding that you're probably most familiar with. If it is 4 or below, I don't round. If it's 5 or above, I go ahead and round. So since 7 is more than half, I would use that to round the 4 up to 5. So 1.6478 becomes 1.65. Okay, the value after the 4 is greater than half. Round it up. Okay, so just a reminder, round down if the last digit being dropped is 4 or less. Okay, so when I talk about the last digit being dropped, that's that leftmost place. Round up if it is 5 or more. Okay, now, the rules keep coming on this. We have to look at how do we apply the rules within a calculation. How do I use the values in a calculation to determine the number of significant figures in the final answer? Well, unfortunately, it's a different set of rules depending on what mathematical operation you're carrying out. The easiest one to look at is if you're multiplying or dividing. So we're going to look at that rule first. If you carry out a multiplication or a division within a calculation, the result will carry the same number of significant figures as the factor, the value, with the fewest significant figures. Okay, so what we're going to do is look at the numbers in the problem, count how many significant figures in each one, and take the one that's smallest. Let's look at an example of that. I took these numbers, 5.02, 89.665, and 0.10, and I multiplied all three of those together. Now if I punch that in my calculator, I get 45.0118. So how do I know? Do I use all of those numbers? Do I use part of those numbers? I have to go back to the numbers that I used in the operation. I count the number of significant figures. 5.02 has 3 significant figures, the zero sandwich there. 89.665, no zeros in there, they all count, 5 significant figures. And then I look at 0.10. They got tricky here. They had a leading zero. The leading zero doesn't count, not a significant figure. That's just a placeholder, it's just there so that you can see the decimal point a little easier. But now this zero is a trailing zero after a decimal point. That one does count. If it didn't count, I could just write 0.1. Okay, so I have to count these two. These are my 2 significant figures. Now I look at how many I counted. 3, 5, 2. Smallest one here is 2. Since this is smallest, 2 significant figures, my final answer can only have 2 significant figures. Doesn't matter where the decimal points are for multiplication and division, only the number. So I only keep the first 2, 45. Now, the next one is the one I use to determine rounding. So the 1, and the 8 have nothing to do with rounding. I look at the 0. That is not greater than 4. It's not 5 or above, so I would not round the 5. I would just cut it off, round it off to 45. 2 significant figures. Okay. Now let's look at division. Let's say I take the number 5.892, divide it by the number 6.10, and my calculator tells me 0.96590. Right, there's my intermediate number. Where do I round it? My first number has 1, 2, 3, 4 significant figures. This one, it's got a trailing 0 after a decimal point, so 3 significant figures. 3 is the smaller number. My final answer has to be rounded to 3 significant figures. So right here, this is a placeholder 0. It's a leading 0, so it doesn't count. So I don't start counting significant figures until I get to the 9. 9, 6, 5. Those are my 3 significant figures. Now I look at the next number, the 9, and use that for a rounding determination. 9 is greater than 5, so I would round this one up. 966. Now the other operations I could carry out, in addition to multiplication and division, are addition and subtraction. Addition and subtraction have their own set of rules, and this is the one where people tend to get messed up. Because in addition and subtraction, the results, the final result, will carry the same number of decimal places as the quantity carrying the fewest decimal places. So here, I don't care about how many significant figures there are in each of the numbers that I started with. I'm only looking at the number of decimal places. Got to keep that in mind. Let's look at what we're talking about here. All right, so here's an addition. We took 5.74, 0.823, and 2.651, and we added them all together. Okay, again, in my calculator, I get 9.214. What do I do here? Well, I have to look at where I have the least number of decimal places. Now here's a hint. When you're doing addition and subtraction, a lot of people want to write them out in a single line. So they would write 5.74 plus 0.823 plus 2.651 equals. They've got them all in a line like this. That's okay if you know how to look at it and see the number of decimal places, but if you can't see that easily, you may find it helpful to put the numbers stacked in this manner, line them up on the decimal point, and then draw a line immediately to the right of the number with the fewest decimal places. So in other words, take a line and move it until you get to the first point where one of the numbers doesn't have any other numbers to the right of that line. So in this case, if I started with my line and moved it, as soon as I got past the 4, there's no other number here to move past, so I have to stop. Okay, that's my cutoff point. I look down here, 2 decimal places, so 9.21. The 4, not big enough to round up the 1, so I leave it as 1, 9.21. Let's look at another example with a subtraction. All right, in this case, I had 4.8 minus 3.965. Punch it into my calculator, I get 0.835. Where do I cut that off? All right, so if I stack my numbers like this, and then I draw my line and move it over, boom, I get to the right-hand side of the 8. There's nothing else. I have to stop. So basically what you can do is move your line from left to right until somewhere in one of the operators there's no other number to move past. That's your stopping point. Okay, so this is telling me I can only have the 1 decimal place right down here, 0.8. 3, not high enough to round that up. Don't worry about the 5, only the 3. 3 is not high enough, so I leave it as 0.8. Okay, now, what happens if you have a calculation that involves different sorts of operations? It has both a multiplication or division and an addition or a subtraction involved in it. And yes, we will see those. Okay? Now, if that happens, you will have one operation that's in parenthesis, most likely. So whatever is in parenthesis, it's telling you to do that step first. That's a mathematical thing anyway. You do that first and then determine how many significant figures that step would have. Now you don't round the number. Don't round it up or don't round down. You keep them all. You just remember how many significant figures it limits you to. Then do the remaining step and then apply the rule. So in other words, you have to apply whatever set of rules go with the number that you do first and then apply the final answer. But when you're determining the actual number, you would just punch everything in your calculator. Don't worry about rounding. Do all the operations, keep the answer, keep it rolling through. So again, we'll look at an example of that. So in this example, we see the calculation 3.489 times the value 5.67 minus 2.3. Now in this case, the subtraction is going to be done first since it's in parentheses. So we apply that first, 5.67 minus 2.3. Now if I line those up, I would see that I have to stop at the tens place. The line would stop right after the 3 in 2.3. So my value is 3.37. What I need to remember is that this one would get cut off at 3.3. Now normally, if this were the last value, I would round it to 3.4 and stop there. But I don't want to do that. I want to avoid those small errors that compound as I do my calculation, so I'm not going to round it yet. I'm going to keep the 3.37. I'm just going to underline the least significant figure where I would stop. I would stop at the tens place, the 3. Now I'm going to take the answer that I got, the 3.37, and multiply that by the 3.489. So I carried out this step, got my value, bring that number right down here, put it back in. So 3.489 times 3.37, calculator gives me 11.752. Now I remember that multiplication division uses least number of significant figures. 3.489 has 4 significant figures. 3.37, even though I've got the whole number written, this underline is telling me that that number had to be cut off after the tens place, which would have been 3.4. It would have had only 2 significant figures. But now I go back to my rule for multiplication. 2 significant figures, 4 significant figures. Final answer only has 2. Okay, so I cut it off right here at the second significant figure. 7 is greater than 5. Rounds that one up. Okay, so final answer would be 12. Again, if you need some help on this, if you need more work on that, we will look at this in scientific math. I can give you plenty of examples, plenty of practice on that one.